next we're going to talk about limits. Now, limits are really the beginning of calculus. And actually, everything we're going to do this semester is based on limits. And we're going to see graphical understandings of limits and algebraic understandings of limit. Both of them are pretty important, well, very important in calculus. Calculus 1, 2, and 3. So let's start with an informal definition of limit. And we'll use a graph to interpret this. Definition: let f be a function and let L be a real number. Okay? If all values of f of x approach L as the values of x approach A, then we say the limit of f of x as x approaches A is L. And this is a lot of words, so we write that as limit, L-I-M, as x approaches A, x with an arrow, A of f of x equals L. So if all values of f of x approach L as x approaches A, as all values of x approach A, then we say the limit is L. And we're going to start with some graphs and interpreting that using graphs. So let's look at this function. This is just a random function, and I marked off the point 3, 4. Sometimes I draw dotted lines to make the points absolutely clear. That's all these dotted lines mean. And here, we want limit as x approaches some x value. The only x value we have here is 3. So let's find, if it exists, limit as x approaches 3 of f of x. Now, I marked off 4, so you might think the answer is definitely going to be 4. It will be. But why? Well, what does the definition say? If all values of f of x approach some L as the values of x approach, in this case, 3. Remember, we have x values on our x-axis. How can we approach 3? On this x-axis, how can we approach 3? I see two ways on the x-axis that we can approach 3. This way, we can approach 3. And this way, we can approach 3. Okay? So we have two different ways of approaching 3. If all values of f of x approach L as the values of x approach 3. Well, this part of the sentence is talking about what happens regarding x values, what happens on the x-axis. This part is asking about what the function does, what the y values of the function do as these x values approach 3. Well, what does the function do as x approaches 3 on this side? What does the function do? Well, it approaches right there. As x approaches 3 here, this function approaches whatever that point is. As x approaches 3 over here. Okay? There are multiple ways of approaching 3. Just because we have something happening on one side doesn't mean that's all we have to consider. We can also approach 3 over here. What does the function do as x approaches 3 over here? Well, it does something like this. And you'll notice, as x approaches 3 in any way it can, this function approaches this point. And in particular, the values of f of x, y values, approach, in this case, a y value of 4. So these values of f of x, which are y values, approach 4. So the limit, as x approaches 3 of this function, is 4. Let's look at another example. Let's mark off 4 again. I'm again going to do that dotted line thing to make it absolutely clear where we are. But instead, instead of having a function in one piece there, I'm going to put this other point up here. So in this case, f of 3 happens to be 6 because there's a hole here. But what is the limit? Limit. We're still going to find, or try to find, well, find, by trying to find, the limit as x approaches 3 of this function. And again, we still have these two ways of approaching 3. We have that way, and we have that way of approaching 3. If all values of f of x approach L as x approaches 3 in either of those directions, then the limit is that number, that L. Well, what happens to the function as x approaches 3? Well, let's look at the function as x approaches 3. As x approaches 3, the function looks like that. It approaches this open dot as x approaches 3. On this side. We haven't looked at this side yet. What happens on this side? Well, on this side, the function again approaches that open dot as x approaches 3. Values of x approach L as x approaches 3. What would our L be here? Well, on this side of 3, this function is approaching 4. On this side of 3, this function is approaching 4. So the limit as x approaches 3 of this function is 4. Now, I imagine many of you are thinking this answer would be 6. So I'll note, even though f of 3, yes, is 6. F of 3 is 6. But why is the limit not 6? Well, this limit doesn't say it matters what happens at 3. This limit is using the word approach for everything. This limit is not concerned with what happens at 3. In none of this discussion did what happens at 3 matter. All that matters as far as the limit is concerned is what happens close to 3. What happens on this side of 3 and what happens on this side of 3. It does not matter what happens at 3. Let's do another. What's the third example I have here? Example. Let's consider the graph y equals f, or y equals x, or f of x equals x, maybe I should say. And let's draw the graph here. Now let's draw it here. I'm just going to mark off a point. Let's mark off 2 and 2. And here we want limit as x approaches 2 of f of x. What do I want to write? Thing I write after this. So here we want the limit as x approaches 2 of this function. Well, again, we have two different ways of approaching 2. That way and that way. And this function, as x approaches 2, here, y approaches 2. In this function, as x approaches 2 over here, y approaches 2. So no matter which way we approach x equals 2, the function approaches y equals 2. And in general, for this line, y equals x, the fact that this is 2 doesn't matter. It could be any number. So I'll say, and in general, limit as x approaches a of this function, f of x equals x, we could just rewrite that as x. In general, limit as x approaches a of x equals a. So if this were like -3, as x approaches -3, it would y would approach -3 from both directions. Let's look at two more examples. How about a horizontal line? Horizontal lines are functions because they satisfy the vertical line test. Vertical lines are not functions because they don't. Horizontal lines are written in the form y equals some number or f of x equals some number. So example, consider f of x equals 4. This is just a horizontal line at height 4. So I'll draw that like this. Let's mark off 4. So here's f of x equals 4. Maybe I'll label it f. And find limit as x approaches, I don't know, 3. 3 is a good number. Yeah, okay, 3 is a good number even though it was the first example. Well, again, there are two ways of approaching 3. We could approach 3 over here. We could approach 3 from over here. What does the function do as we approach 3? Well, here, the function approaches that point. And over here, the function also approaches that point, which occurs at y equals 4. So that limit is 4. And just like this one, that generalizes. This 3 could have been any number. It could have been -2. It could have been pi squared. It could have been 0. No matter which number we chose for this constant function, by an argument just like this, the limit would be 4. So we'll say, and in general, limit as x approaches a of, in this case, f of x equals 4, equals 4. No matter which x value we choose, that limit would be 4. Let's look at another example. Example. Consider this function. These are all functions. They all satisfy horizontal vertical line test. Consider this function. What is this limit? Well, we have to remember the definition of the limit. I didn't need to erase that. We need to remember the definition of the limit. The limit says if the values of if the values of f of x approach L as x approaches A, excuse me, then the limit as x approaches A, in this case 2, of f of x is L. Well, again, we're going to look at different ways of approaching 2. Well, what happens? Well, we have one side of 2. We have another side of 2. There are two different ways we can approach 2. If we approach 2 over here, what does the function do? Well, it approaches this open dot, which is at y equals 5. Okay. So if we also get 5 by approaching 2 the other way, then the limit's 5. But what happens as we approach 2 on the other side? Well, where's the function? It's somewhere up here. As we approach 2, from the other side, the function approaches y value of 7. 5 and 7 are not the same number. So we needed all values of f of x to approach some L as x approached a in any way. And in this case, if we approached 2 from this side, we got 5. If we approached 2 from that side, we got 7. And when that happens, we say the limit does not exist, which we'll abbreviate dne. Now, this example suggests that it might be useful to describe limits by looking at both sides. Actually, all of these examples suggest that it might be useful to describe limits by looking at both sides, and we will do that. We have this definition. We write limit x arrow a with a positive sign as a superscript on a. Limit as x approaches a from the right is what this positive superscript on a means. It means we're looking at what happens to the right of a. So that limit is L, and we say the limit of f of x as x approaches a from the right is L if the values of f of x approach L for x values approaching a with x larger than a. So we're just looking at the right of a for this limit. Similarly, we have the same definition for the left of a, but we have a negative sign as the superscript on a. So similarly, this limit would be limit as x approaches a from the left is L if the values of f of x approach L for x values approaching a with, for the second one, x on the left of a, so x less than a. And that's with the number line thinking. X larger than a is on the right of a, x smaller than a is on the left of a. So in the first few examples, all of the limits on the left and right would have been the same number. But in that last example we did, where the limit didn't exist, the limit on both sides of 2 did exist. On the right of 2, it was up there, the limit was 7. On the left of 2, the other piece that approached the open dot, the limit on the left of 2 was 5. And there's an important theorem in math using just these definitions. Limit as x approaches a of f of x is L if and only if. In math, that means it is logically equivalent. It means this piece implies this piece and this piece implies this piece. We will use this to find some limits. But the limit as x approaches a is L if and only if the limit on the right is L and the limit on the left is L. So I just wrote that as limit as x approaches a from the right of f of x is L, and that equals the limit as x approaches a from the left is L. And this is for L, a finite number, real number. And we'll use this a few times throughout the semester. But it's nice to have a graphical understanding of these limits. And the most important graphical understanding is actually one like this. Maybe that second example. That one's pretty important, the one with the hole at 3/4. But for now, we will stop our understanding of the graphs of limits at this until we see more examples in the future. And we will transition over to algebraic understanding of limits. And the first thing we will do algebraically is look at the page on Canvas called Algebraic Limit Laws. I don't know if it shows up on the camera. Algebraic Limit Laws. So this page identically is on Canvas with, 7 rules. So I'm just going to point at it here. You can look at it on Canvas. Algebraic Limit Laws. Let f and I hope this shows up. Maybe I should put another light on. Do I have another light? I have an overhead light which glares in the board, so I don't use it. Maybe that, I don't know, I hope that helps. I hope it made a difference. Algebraic limit laws, let f and g be functions. We actually talked about the first two. Limit of a constant as x approaches a is that constant. We saw that in the example with f of x equals 4. Second one we saw in the example f of x equals x, y equals x. Limit as x approaches a of x is just a. So we already saw those. These other 5 rules we will use. We haven't seen them yet because we haven't done limits algebraically. But let's look at them. Rule 3. Limit of f plus or minus g is limit of f plus or minus limit of g. So if you have a limit of 2 things added together, you can take the limit of one piece and then add it to the limit of the other piece, or subtract, if it's subtract. Fourth rule, very important. Limit of a constant times a function is a constant times the limit of the function. So if you have a constant in front of your function and you want to take the limit, you can just pull that constant out front and then take the limit. Very important. The next 2 rules, 5 and 6, if we have a product of functions and we want the limit of the product is the product of the limits. That's useful. Rule 6, if we have a quotient, the limit of a quotient is the quotient of the limits, provided the denominator is not 0. If the denominator is 0, the quotient won't exist. And what's the 7th? The 7th is if we have an exponential, or not an exponential, if we have an exponent, we can take the limit by pushing the limit inside the exponent, and then taking the limit on the inside, and finally taking the exponent. So hopefully you followed along with the page posted on Canvas. But right now, we will do a few examples using those directly, and then we'll see how we can use them indirectly. Many of you will probably prefer the indirect use to the direct use, but I would like to illustrate the direct use first. So let's do a couple examples. It'll be useful to have that page of limits nearby because I am going to reference them by number. Let's just do one example, actually. Example. Compute this limit. You could do a graph and label some points if you want of this one. I would recommend against that. Limit as x approaches 2 of x squared minus 5x plus 3. I'm going to throw that in parentheses so it's clear that the limit is on everything. So we want this limit. We have a polynomial, we have a function. This function consists of 3 things added together. And one of them is added with a negative sign, but it's still added. If we have 3 things added together, we can use rule 3 to smash it apart into 3 limits. Where will I do that? Let's do that here. Equals, using rule 3, limit as x approaches 2 of x squared minus, remember if it's a negative you carry the negative out, limit as x approaches 2 of 5x plus limit as x approaches 2 of 3. And that's just using rule 3. Rule 3 says if you have 3 things added together, you can do them one at a time. Well, what can we do next? Well, we have 3 limits. You might think that it made it harder because we went from 1 limit to 3 limits. I may agree. But let's do the first limit, and then we'll do the second limit. What can we do with that first limit? We have x squared. Well, what do our rules say? Maybe I should look at the rules. What can we do with x squared? Well, if you look at rule 7, if n equals 2, you can put the limit inside that square. So we'll say equals, I'm going to put 3 numbers on this. So I'll first write rule 7 up here like this. By rule 7, we can rewrite this first piece as limit as x approaches 2 of x all squared. We can force the limit inside the square. How about this next piece? Well, we have 5x. What can we do with that? Maybe I should just leave this like this so that I don't have to keep flipping. What can we do with 5x? Well, let's first not forget that negative sign. That would not be a good idea to forget that. What can we do with 5x? Well, if you look at rule 4, that tells you how you can deal with a 5 in front of some function. Rule 4 says you can take that 5 outside of the limit. So we did that. Well, let's finish this one and then I'll say what I was about to say. What about this last piece? Limit as x approaches 2 of 3. Well, if we look at our list of rules, we can apply rule 1 to that. Rule 1 says the limit as x approaches some number of a constant is that constant. So here x is approaching 2. Well, as x approaches 2, 3 doesn't change. So that limit is 3, and we used rule 1 on that piece. Well, okay, we still have 2 limits we have to deal with. How can we deal with those 2 limits? Well, let's start with this one. We have limit as x approaches 2 of x. Does that show up anywhere? Well, gee, it shows up right there in rule 2. Rule 2 says limit as x approaches 2 of x is 2. Okay? So that equals 2, and it's still squared. What about this next one? Well, let's write the 5 first, and the negative. Negative 5, well, if we get rid of that negative 5, we again just have limit as x approaches 2 of 2, which by rule 2 is 2. 3 is still 3. Well, now we just have to combine these numbers. What do we get? 4, negative 10, positive 3. So that's negative 3. 7 minus 10. And let's check my answer to make sure I didn't do something wrong, and I guess I didn't. So right here we used 5 of the rules. We did not use the quotient or the product rules, but their use is very similar. Like if you had limit of x times, I don't know, x squared plus 5x, limit as x approaches 2 of x times x squared plus 5x would be the limit as x approaches 2 of x times limit as x approaches 2 of x squared plus 5x, and then you use the rest of the rules. And similarly for a quotient. But notice 2 things. 1, if you interpreted that negative as, if you interpreted this negative 5x as a positive, well, as adding a negative 5x, you'd get a positive here and a negative here, and then you'd pull out a negative 5 using rule 4 again. But one other thing to notice, we did 3 steps of work, technically 5 steps of work if you count those last 2. We did a lot of work, but what would happen, well, let's look at this step and this step. We used 5 rules to get to that step. Could we have done that in fewer than 5 rules? Yes. How could we have done that? Well, look what we have. We have x squared minus 5x plus 3. 2 squared minus 5/2 plus 3. All we did in applying these 5 rules was explain why, or show why, we could just substitute x equals 2 into this limit. And these algebraic limit laws allow us to do that. So right here, you don't necessarily have to show all of these steps. This is just a first limit example explaining the limit laws. But right here, using the limit laws reduces to just doing a substitution of this number in for x. You substitute x equals 2, you get 2 squared minus 5 times 2 plus 3, and that's what you get. So let's consolidate that observation as a theorem, which is not stated directly in the textbook. And here we have this theorem. For general f of x and g of x, upon direct substitution, the limit as x approaches a, f of x over g of x. So we have a quotient. G of x could be 1, so this could just be a polynomial. But in general, we have the limit of this quotient as x approaches a. If you substitute, you will arrive at a number or an expression which takes one of the following forms. Now here, this pound sign stands for any non-zero number, and 0 stands for 0. So you have a fraction, you direct substitute this a, and you will arrive at one of the following forms. 0 over a number, a non-zero. Non-zero number over non-zero number. 0 over 0, or non-zero number over 0. You'll always get one of those forms upon direct substitution for an appropriately written fraction. Now, if you arrive at case 1 or 2, 0 over number is just 0. Number over number is just a number. In those cases, that simplified fraction is the limit by the limit laws. If you get 0 over number or number over number, that simplified fraction, 0 or whatever that number is the limit. Case 3, if you do a substitution and you get a 0 over 0. Here, you'll do algebra on f over g until the 0 over 0 goes away and you're left in case 1 or 2. We'll see a couple examples of that. Here, if you get a number over 0, what you'll do is analyze both sides of a. So we'll look at the limit on the left of a and the limit on the right of a, and we will interpret it from there. So let's look at some examples of all 4 of these cases. So let's do a few limits. Limits. Cases, well, I'm going to go in order because cases 1 and 2 are much quicker than case 3 and 4. So I'll start with these 2 limits. Example, compute these limits. So first one, and the second one. So compute these limits. This theorem I just wrote says that the first thing you should always do is a direct substitution, unless you want to go through a limit law argument. If you go through a limit law argument, you might find yourself in case 3 very annoyed with all the work you did to get there. First thing you do with any limit is a direct substitution. It will make your lives much easier. Well, it will make calculus much easier. First thing to do is a direct substitution, and I'll just write that here. What happens on a direct substitution? Well, you get negative 3 plus 3 over negative 3 minus 3. Okay? That's 0 over negative 6. 0 over negative 6 reduces to 0. Once you get here, you know you're in case 1. In case 1, your limit will be 0, because that fraction reduces to 0. And in using that theorem with those 4 parts, I bypassed all the limit laws. If you wanted to use limit laws, you'd need, what, Rule 6, then you'd need Rule 3 a couple times, then you'd need Rule 2, and then you'd need another Rule 1 probably twice. Or you could just use that theorem. Okay, how about this next one? Well, again, we're going to try a substitution, because if we arrive in case 1 or 2, then we're done. So I'm going to write the substitution here. Let x equal 3. What do we get? 4 times 3 squared minus 3 times 3 plus 2 over 3 minus 7. Okay. 4 times 9 is 36. 36 minus 9 is 27, plus 2 is 29. 3 minus 7 is negative 4. So I'll write the negative outside there. So this right here, negative 29 fourths, is the limit. Maybe I'll make the negative a little larger. And in this case, oh God, I can't write anything. And in this one, We did our substitution. We got number over number. That's case 2. These directions should have said, compute the limit or evaluate the limit or something like that. Let's do 2 more. When you have a limit, first thing you should try is a direct substitution, because if that works, you're done. If it doesn't work, well, you have more work to do, but at least you know that you didn't jump over a quick answer. Evaluate these limits. Which one? Let's do these 2. Limit as x approaches 2 of x squared minus x minus 2 all over x squared plus x minus 6. We're going to do 2 limits. I will write the second one after finishing this first one. Not positive how much room this first one will take. The second one will take a good amount of room. So evaluate the limits. This will be first. There will be a second one. Again, try a direct substitution and hope it works. What do you get if you do a direct substitution here? 4 minus 2 over 4 plus 2 minus 6. So what is that? 0 on top and 0 on the bottom. Well, 0 over 0 is not a number. 0 over 0 is an indeterminate form, which can behave in the limit like anything. But once you do a substitution and you get 0 over 0, well, rule 3, or case 3 said, do algebra until the 0 over 0 goes away, and you're in case 1 or 2. What does that all mean? Well, let's try doing some algebra. What can we do with this? Well, we have 2 degree 2 polynomials. Maybe we can factor them. Let's try factoring them. What do we need? Numbers which make 2 and 1, or negative 2 and negative 1. So what? Negative 2 and positive 1. Negative 2 and positive 1 make negative 2. Negative 2 and positive 1 make negative 1. Should be 1 fraction. I don't like writing on that seam. So does that factoring work? Yes. How about the bottom? We need numbers which make 6 and 1. Well, 2 and 3 make 6. 2 and 3 make 1. And the negatives work out nicely because we need a positive 3 and a negative 2. So the top and the bottom both factor. This right here is an equal sign. In math, an equal sign is used when one thing equals the other thing. Right here, that equal sign is wrong. What is on the one side of that equal sign is different than what is on the other side of that equal sign. Right here, we have the limit of some expression. The limit of some expression isn't just equal to a bunch of numbers and x's. The limit of some expression is equal to a bunch of numbers and x's after you take the limit. Before you take a limit, if you want your equal signs to be correct, which we do, you need to write limit. Because the limit of this expression does equal the limit of this expression, because these expressions are the same. This and that are the same, just rewritten. But we have not taken a limit. We have not applied the limit laws. We have not done cases 1 or 2. Well, what can we do with this? Well, we have the limit of some fraction, but look at this. That's in the numerator and the denominator. Well, isn't that wonderful? We can now simplify that fraction. Which we did. We can simplify that fraction into just x plus 1 over x plus 3. But we still have not taken a limit. So we need to continue writing limit until we take the limit. When do we take the limit? Well, we take the limit when substitution works. When the limit laws have been applied. What happens if we substitute here? Well, you get a number over a number. You're in case 2 now, so you can take the limit. Notice this equals sign, once we did the substitution that worked, we were allowed to remove the limit. We took the limit in going from this step to this step. And we have the limit of 3/5. So here, the algebra we did when we wound up in case 3 was factoring. Factoring worked here. And we got a number as our answer. I think there was something else I wanted to say about this. Maybe not. It'll come back to me. Let's do another example. So evaluate this limit. This is one fraction. I don't want to write too much on the seam because it may damage the seam a little. Limit as x approaches -4 of root x plus 13 minus 3 over x plus 4. Well, again, we hope a direct substitution works. Does it? Well, let's try. Well, we see that 0 on the bottom. We already know something's not going to go well. But let's see if we're in case 3 or 4. What's on top? Well, we have root 9 minus 3. So we get a 0 over 0, and we're in case 3. Well, now we have to do some algebra. Oh, that's what I wanted to say. In the previous example, well, in case 3 I wrote until the 0 over 0 goes away. Well, let's just do this example. Same type of thing. What did I mean by the 0 over 0 goes away? Did you see it in the previous example? Well, if you didn't, you will in a moment. Right here, I can't factor this. Maybe you can factor this. I can't. But what we can do, there are a few ways we can rewrite an expression without changing it. What does that mean? Well, something plus 0 is the same as that thing. Something times 1 is the same as that thing. So if we want to leave an expression unchanged, we can either add a 0 or multiply by a 1. When completing the square, we saw how it could be convenient to add a 0. Here, we're going to see how it can be convenient to multiply by 1. Which one will we multiply by? That one. That is something divided by itself, so it reduces to 1. So right here, if we compute this limit, it's the same as computing the limit we wanted, because multiplying something by 1 leaves it unchanged. Now, where did that 1 come from? Well, we looked at this numerator, we looked at this negative sign, and we changed it to a positive sign. we multiplied and divided by that. We can't just multiply by that. If we just multiplied by that, we'd be changing the problem. But by multiplying and dividing, we multiply by 1, which does not change the problem. Now, why is this a convenient one to multiply by? Well, let's see. What we're going to do here, with these, they will all, in general, work out in a specific way. So in this case, in the denominator, I'm not going to factor anything, and we'll see why in a moment. So I'm just going to write it as it is. Sorry, my floor is being loud. It's an old house built in the 40s, so the floor is a little loud. So we'll leave the denominator as it is, plus my microphone's on the floor. I don't know if I mentioned that yet. The microphone right here unceremoniously dropped on the floor in front of me. Oh, I hope that didn't make a noise. But what can we do with the numerator? Well, we can multiply the numerator out. What does it equal? I'll tell you what it equals. It equals that. Why does it equal that? Why does it equal that? Well, if we remember a nice algebraic result from algebra, if you have a minus b times a plus b, that just equals the first thing squared minus the second thing squared. And that's what we have in the numerator. We have something minus something times that same thing plus that same thing. And we can multiply them as the first thing squared, x plus 13 under a square root all squared, is x plus 13. Square roots and square cancel. Square root and square are inverse functions. And what about the second thing? Well, we have minus b squared. What's b? b is 3. So we subtract 3 squared, which is 9. So when we multiply by that convenient one, we will have a simplification like that. Well, how does that help us? Well, I'm going to be a little lazy, because that denominator is a pretty big denominator. In this numerator, we have x plus 13 minus 9. 13 and negative 9 make a 4. And what can we now do with this? Well, look at this. There's an x plus 4 on the top, and there's an x plus 4 on the bottom. So we can reduce that fraction. So I'll say equals limit as x approaches negative 4. What's left on top? Nothing except a 1. Left on bottom, root x plus 13 plus 3. We did all this algebra, and then these x plus 4's canceled. And now down here, we hope, after doing all that work, that we could do a substitution. And we can, because we get 1 over 3 plus 3, which is 1/6. Now, in case 3, it says, do algebra until the 0 over 0 goes away. I see this step as the 0 over 0 going away. Now, that technically doesn't happen. We're not saying 0 divided by 0 is 1. Because remember, the only time that these are 0 is when x equals exactly negative 4. But remember, the limit doesn't care what happens when x equals negative 4. The limit cares what happens on both sides of negative 4. What happens at negative 4 is meaningless as far as the limit is concerned. And because of that, close to negative 4, this divided by that is always 1, even though at -4, this divided by that is not 1. It's 0 divided by 0, which is not a number. And in the first example, the same thing happened when we had an x minus 2 divided by an x minus 2. So we have two limits from case 3. There are a couple different forms a case 3 limit could equal. Like you could have like a fraction divided by a fraction or something. And the algebra in that isn't, I mean, there's nothing clever like this. You just have to be careful when writing the fraction as one fraction. So that one will be on the worksheet, and that's definitely worth trying because you do have to organize fractions, which can be annoying. It is pretty annoying to organize fractions, but it's a good process to go through. Now, we've handled cases 1, 2, and 3. Before doing an example in case 4, let's make an observation. So first, we're going to look at the graph of what f of x equals 1 over x, one of our basic functions. We're going to make these observations. We're actually going to use this to begin our interpretation of what infinity means. We want to look at these two limits. Limit as x approaches 0 on the right, and limit as x approaches 0 on the left. Well, this isn't defined at 0, but that doesn't matter, because it's defined on the right and left of 0. So what happens on the right of 0? Well, we're looking over here. What does this function do on the right of 0? Well, it keeps going up. It keeps increasing without bound. It keeps getting larger. It gets larger than any finite number. When that happens, the limit is infinity. In this case, positive infinity. If you don't write the positive, it's assumed positive. On the right of 0, this keeps going up, and it gets larger than any number, which is what we mean by infinity. Not quantity, it's a symbol which stands for something which gets larger than any number. What about the left of 0? Well, we're looking over here. We're looking over here. What happens on the left of 0? Well, this keeps going down without bound. It keeps going down. It gets smaller than any negative number. And in that case, we say that that limit is negative infinity. And we're going to keep this interpretation in mind, because with this, 1 over 0, so 1 over 0 is a fraction. It is not a number. But just by looking at this graph, we can see that as that denominator goes towards 0, which is what we're doing in limits, as that goes towards 0, that fraction behaves like a positive or a negative infinity, depending on, what sign you're looking at. And we're going to use that observation to analyze the limits which take the form described in case 3. Now, these two limits were different. If I drew 1 over x squared, you'd get this limit on the one side is positive infinity, limit on the other side is positive infinity. So you could do an analyzation, that's not a word. You could, there's probably a noun for analyze that's just escaping me right now. You could analyze both sides and get the same sign on infinity, or you could analyze both sides and get a different sign on infinity, depending on if what you're dealing with looks like that, or even one that goes to negative infinity on both sides. But let's look at some examples. Whenever you get a number over 0, first step is look at both sides, because you might be able to say a lot about the limit. Example, evaluate Well, yeah, evaluate the limit. And let's say if it exists. If the limit on both sides is infinity, we will just say the limit's infinity for convenience. Same for negative infinity. If it's different, we'll say it's non-existent. So let's do this limit. Limit as x approaches 2 of x minus 3 over x squared minus 2x. Well, first thing to do is try a direct substitution. So we get a number over 0. We are in case 4. So what we're going to do is look at left of 2 and we'll look at the right of 2. I guess I'm contradicting myself right now. I said that's the first thing you should do. If you can factor this, that's actually the first thing you can do. You should do. And I will factor it. Once it's factored and you get a number over 0, then you jump to both sides. When it's factored, the thing that causes the 0 in the bottom really pops out. So we get a number over 0. So we analyze both sides of 2. And we'll do that here. Limit as x approaches 2 on the right of x minus 3. We'll use the factored form. We'll see why in a moment. And limit as x approaches 2 from the left of that. So let's do the limit on the right first. Now, we know, just from getting a number over 0, we know on one side it's going to be a positive or a negative infinity. We know on the other side it's going to be a positive or negative infinity. What we need to do is figure out if this is positive infinity or if this is negative infinity, and if this is positive infinity or negative infinity. So all we really need to do is find the sign of the infinity. And having the factored form is quite convenient for finding that sign. So I'm going to use math notation to my advantage here. What do I mean by that? Well, all we care about is the sign. And in this first limit, we're looking at the right of 2. Well, we know it's going to be an infinity. Let's write an infinity. All we have to do is figure out the sign. Well, we have 3 things here multiplied together. And some are divided, but I mean, they're all multiplied. Positive times positive is positive. Positive times negative is negative. Negative times negative is positive. We're going to use that to our advantage. And I'm going to introduce notation I've never actually seen anywhere else, but I find it helpful. Remember, we're looking at the right of 2. So we're looking at numbers really close to 2. I mean, 3 is way over here. We're looking like 2.001, even closer to 2 than that. So we're really close to 2, but on the right. What happens when we substitute into the top? Number really close to 2 on the right, minus 3, is a negative. I mean, the fact that it's a number doesn't matter. The fact that it's a negative, when you substitute a number to the right of 2 up here, the fact that that's negative is what matters. And let's do that on the bottom. This first piece, x, on the right of 2, substitute into x, you'll get a positive number. And for this last term, this x minus 2, substitute numbers on the right of 2, so numbers like right there. That number, those numbers, minus 2, is positive. Are positive. So substitute up here a number very close to 2 on the positive side, you get a negative. Substitute a number very close to 2 on the positive side of 2, you get a positive and a positive. So overall, we have 1 negative. So that tells us the limit on the right of 2 is negative infinity. Okay? We have to analyze the other side of 2, and we'll do it the same exact way, but instead of looking at the right of 2, we'll look at the left of 2. So numbers like 1.99 and closer to 2. Well, again, we know it's going to be an infinity. We just have to figure out the sign. Numbers to the left of 2 but close to 2, like 1.9-ish numbers, substituted in the top, again will be a negative. Numbers close to 2 on the left of 2, substituting for x, give us a negative. Give us a positive. I was looking at that negative sign, I just said negative. Numbers on the left of 2, substituted in for x, you'll just get that number, which is positive, because it's very close to 2. Numbers to the left of 2, substituted in there. Well, numbers to the left of 2, minus 2, bring you on the negative side of 0. Bring you to the negative side of 0. So numbers like 1.99-ish type numbers, minus 2, are negative. So here we have 2 negatives and 1 positive. So that limit is positive infinity. Now if you went through this analysis and you got the same sign on infinity, we would just say this equals whatever that infinity is. But since we got different ones, we'll say this limit does not exist. And we'll apply that left and right limit theorem, even though it doesn't technically apply with infinities. But we will, that's okay. So we got number over 0, looked at both sides of 2, found the signs of infinity, and interpreted. Let's do another. Oh, I should have left those directions there. Evaluate the limit if it exists. That one didn't exist. We had to do a good amount of work to show that it didn't exist, though. X over x minus 3 squared. We'll do 2 more, including this one. X over x minus 3 squared. Again, you might suspect we're in case 4 because I'm working in case 4, but you should always check direct substitution. Because if that works, you're done. So here, we get a number over 0. So we're in case 4. This is already factored as much as it can. So we can jump straight into both sides. Let's say we analyze both sides of 3. Because that's where we're taking the limit. And I'm going to set myself up a lot. Sometimes my infinities have a gap. That's okay. I write my infinities like this. Sometimes it doesn't work out. I have a lot of trouble drawing like a sideways 8 consistently. A sideways 8 is technically right, but I do the 2 circles right next to each other, or as close as I can get. So let's look at both sides of 3. We have number over 0, so we know these limits are going to be some sign on infinity. Well, which sign? Well, we're looking at 3. The first one, we're looking at the right of 3. So numbers a little larger than 3. Substitute that in the numerator, you get a positive. Substitute in the denominator, what do you get? Well, you get a positive, and then it's squared. Positive squared is positive. So we have positive over positive, which gives us a positive infinity. How about this next one? Numbers to to the left of 3. So numbers that are like slightly less than 3, 2.9-ish type numbers. What happens on this substitution? Well, 2.9-ish numbers into the top, still positive. How about 2.9-ish numbers on the bottom? What do you get? Well, inside the square, you get a negative. 2.9-ish minus 3 is negative. But then you square it. So you could write you could write negative squared down there. I like just taking care of the square by considering it a positive. It gives me less to think about in the next step. So here we have a positive divided by a positive infinity. Positive divided by a positive infinity gives us a positive infinity. Both of these limits are, both sides we get a positive infinity. So we'll say that this limit is positive infinity. Graphically, this would look something like this. Not exactly like that, but something like that. Well, it goes through the origin, but it would look something like that when you have a limit on both sides being positive infinity. And in that case, we'll just say that that limit is infinity. Let's look at one more. Compute this limit. Example, compute this limit, or evaluate this limit if it exists, I should say. Limit as x approaches negative 3 from the right, x plus 2, x minus 7, x plus 5, all over x minus 4, x plus 3, and x minus 10. And let's throw some squares and cubes and things on these. Let's throw a cube up here. Where should I put some square? Let's put a square here. So we have a large fraction with lots of terms, and it's factored. Well, what happens if we do a direct substitution? We still have this limit. The fact that we're looking at only one side, we can still consider a substitution, and if it works, well, then it works. But what happens if we do a substitution here? Number times number times number over number times 0 times number. So you get a number over a 0. Well, that tells you you're in case 4, and you need to consider both sides. Well, we're already considering just one side. I mean, yeah, I could have asked for that limit, but let's just look at one side for now. So with this, we can immediately jump to our infinity analysis, because we're looking at only one side of negative 3 already. Well, let's slow ourselves down with this negative 3. What does the right side of negative 3 look like? The right side of negative 3 looks like numbers over there. So numbers like negative 2.9-ish type numbers. You shouldn't actually write 2.9-ish because the limit doesn't care what happens at 2.9. It cares what happens close to negative 3. I don't need to do that. So what do we have when we try a substitution on these sides? We know it's going to be a sign of infinity. Well, what happens? Negative 2.9-ish type numbers. Substitute in here. What do we get? Negative 2.9-ish plus 2. That's a negative. Cubed. Negatives cubed are negative. Negative 2.9-ish here. Minus 7, well, that's just getting more negative. Negative 2.9-ish type numbers here. Plus 5. Well, that 5 is going to push it positive. Here. Negatives minus 4. Well, that's just getting more negative. Here. Negative 2.9-ish times plus 3. Well, numbers over here, plus 3, are going to wind up on the positive side of 0. And over here, something squared is positive. When you have an even exponent, you don't even have to think about it. You just throw a positive there. Well, what do we get here? 3 negatives. So we have that this limit is negative infinity. You should check for yourselves. The limit on the left of that is the limit on the left of negative 3 is positive infinity. So these limits where we get a number over 0, you always want to check both sides, unless you're already checking one side. Then you don't even need to worry about what happens on the other side. You can go straight to the infinity analysis. So we've covered a theorem which allows us to compute many types of limits. Let's look at another theorem which allows us to compute limits more indirectly.